In section 7.2, we talk about triangle trigonometry. The purpose of trigonometric functions, such as sine and cosine, is to describe the relationship between the sides of a right triangle and its interior angles. We'll start by drawing a right triangle like the one we have here. We have the sides labeled opposite of theta, the side adjacent to theta, and then the hypotenuse, which is opposite the right angle, or the longest side of a right triangle. It's also common to use the following abbreviations for this. Now, one of the things that we really care about are the ratios of the sides of these triangles, namely opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. This gives us the following definition. Assume that we have a right triangle and that one of the acute angles is labeled as theta. Then we can define the following. The sine of theta, denoted sin of theta, is opposite over hypotenuse. The cosine of theta, denoted cos of theta, is adjacent over hypotenuse. And then the tangent of theta, denoted tan of theta, is opposite over adjacent. We can observe immediately that sine divided by cosine, which is opposite over hypotenuse divided by adjacent over hypotenuse, can reduce like a rational expression to opposite over adjacent. In other words, sine divided by cosine is equal to tangent of theta. In Chapter 8, when we talk about trigonometric identities, we'll talk about more phenomenon just like this. We also need to define three more trig functions, which are known as reciprocal identities. First, we have the cosecant of theta, which is 1 over sine of theta, and that turns into hypotenuse over opposite. Next, we have the secant of theta, which is hypotenuse over adjacent. And last, we have the cotangent of theta, which is adjacent over opposite. One more definition is the following. We say that geometric shapes are similar when they have equal interior angles and side ratios. So consider the following two special right triangles, namely the same 30, 60, 90 triangle, where one is simply just scaled up by 2. So what we're seeing here is the following. The triangle on the left has a hypotenuse length of 1, and side lengths of 1/2 and square root of 3 over 2. But if you multiply all of the sides of this triangle by 2, you get the triangle on the right, a hypotenuse length of 2, and then a vertical leg of 1 and a horizontal leg of square root of 3. But all the interior angles are the same, and all the side ratios are the same. This is similar to saying that I have a 65-inch TV and a 75-inch TV. Their aspect ratios should be identical. And even though the side lengths of the TVs will be different, the proportions throughout all the sides are going to be the same. And that's really what we mean by similarity. In this next slide, consider the following two triangles, A and B. Triangle A has a missing side, but we can use the Pythagorean theorem to solve for that missing side. We know that 3 squared plus b squared should equal to 5 squared, where b is the name of the missing side. Solving for b will show us that b is equal to 4, so we have completely filled in our triangle. Then we can compute all 6 trig functions of this triangle with respect to the angle theta. Sine of theta is equal to 3 over 5, cosine is 4 over 5, tangent is 3 over 4. And then our reciprocal identities come as follows. Cosecant of theta is 5 over 3, secant of theta is 5 over 4, and cotangent of theta is 4 divided by 3. Triangle B has an interior angle of pi over 3, which we know is 60 degrees when we convert. We also know that the interior angles of a right triangle, or really any triangle, have to sum to 180 degrees, or pi radians. This allows me to deduce that the other acute angle is 30 degrees, which when expressed in radians is pi over 6. So since this is a 30, 60, 90 triangle, I understand the side ratios as follows. This is clearly expressed in a general way because I have the variable x in every single location, but x is just standing for some arbitrary scalar. But since x shows up in every single side, when I start computing these trig ratios, it will cancel out in every single location. And here we compute the sine, cosine, and tangent of pi over 3 and pi over 6 and obtain the following results. So in this next slide, I want to help you all out a little bit when it comes to computations, because when I type in the characters sine of theta into a calculator, it's already going to have a radian or degree mode set in the background. So when I start plugging in values for theta, I might not necessarily know if my calculator is set to radian mode or degree mode. but whatever the calculator setting is how it's going to understand theta. And the issue is that I might think my calculator is set to radians, but really it's set to degrees. So if I'm not paying attention, I might get a wrong output and not realize it. The idea is that you need to make sure you know what language your calculator is understanding before you type things in. As an analogy, suppose I give you the word burro without any context, and it's going to be a little bit hard to decipher. I need to actually attach a language to this word to pull a meaning from it. But the language that I put on top of this word really determines its meaning, because if I understand it as an Italian word, burro means butter. If I understand it as a Spanish word, then it means donkey. And I know my pronunciation on this isn't fantastic, but the whole point of this analogy is just to understand that you need to attach a language to a word to understand a meaning. Similarly, I need to attach a language to a number to understand its meaning. So when I give you the number 3.67 as an angle, in degrees, it's a really small angle, but in radians, it's a large angle. So until I actually know what unit of measure I'm looking at, or until I know what language I'm speaking in, the number 3.67 doesn't really have a lot of meaning, even when I know it's an angle. Now, all calculators are different, and it might be a little bit hard to tell if it's understanding radians or degrees. So if you can't tell, there's an easy way to test. Type in the value sine of 90. If you output the number 1, then you know that your calculator is in degrees. But if you output the number 0.9, you know your calculator is in radians. Alright, well thank you so much for watching, and join us in our next video in section 7.3 on the unit circle.